Synthesis of Spinosyn A. Spinosyns are a family of polyketide natural products derived from this bacteria here that's found in soil, and they possess extraordinary insecticidal activity. They're important in agriculture because of its efficacy in controlling a wide range of insect pests, whilst also leaving the environment unharmed. This is the full IUPAC name, and I've also hyperlinked the article that I will be referencing. This is the retrosynthetic strategy for the synthesis of Spinosyn A taken from the article. The full synthesis is composed of 31 steps with a number of different types of reactions. Today I will be focusing on 3 reactions, 2 of which are related to these 2 compounds here. So the first reaction will be a hydroboration/oxidation reaction as part of the synthesis of compound 15. I will also go through a Horner-Wadsworth-Emmons reaction between compounds 14 and 15. And finally, a Mitsunobu reaction for the synthesis of this glycosyl imidate. In this reaction, we have our starting material here, which has a terminal alkene double bond. The aim is to substitute this bond with an alcohol group, in turn making this anti-Markovnikov alcohol product. This reaction is comprised of 2 steps, the first being a hydroboration and the second being an oxidation. So in the first step, a sign addition occurs where the electron-rich double bond donates its electrons to the empty p orbital of borane, and this has a tendency to attach onto the least hindered carbon due to sterics. This results in the BH2 and hydrogen to face the same side of the original double bond. It's also important to note that the SME2 is there to stabilize the borane, so it forms only the monoalkyl borane. Next, we deprotonate this hydrogen peroxide with the bicarbonate ion from NaHCO3 to give us H2CO3 and this hydroperoxide ion. This now becomes our nucleophile, which will attach onto the boron of the monoalkyl borane made in step 1. The OH group of the hydroperoxide ion is a good leaving group, which then promotes a 1-2 shift and ultimately results in the detachment of BH2. The oxygen then gets protonated by water, which was formed by the decomposition of H2CO3, and hence gets converted to the alcohol product, which has anti-Markovnikov radioselectivity. Overall, this forms a new bond between the least hindered end of the original alkene and the nucleophile. Also, the oxidation step is stereoretentive. Our next reaction is a HWE reaction between an aldehyde and in this case a beta-ketophosphonate. We form an E-alkene, which is our major product, and we also release a phosphonate ion in the process. So the beta-ketophosphonate has 2 acidic hydrogens on the carbon in the alpha position to the phosphonate group and the carbonyl, which one of them will get deprotonated by this metallic base. This will form a stabilized alkyl phosphonate carb anion, which can also resonate to form an enolate or this cyclic compound here. I will be using this to show how the addition of an aldehyde is at the top face of the ring. As you can see, there is steric hindrance between the R groups of the aldehyde and the phosphonate substituents. This hindrance is favored as larger R groups increase E selectivity. Once the aldehyde has been added, the compound will undergo cyclization to form this trans-oxophosphate. Fragmentation of this will result in the production of this major E olefin, as well as the release of this phosphonate ion. This system is thermodynamically controlled, which also contributes to the high E selectivity. So lastly, I will go through a Mitsunobu reaction, which is essentially the substitution of this secondary alcohol with an acidic nucleophile called diphenylphosphoryl azide in the presence of a dialkyl azidocarboxylate and a triaryl phosphine. So first, the triaryl phosphine will donate its lone pair to one of the nitrogens in dead to generate this anion here. This negatively charged nitrogen will attack the phosphorus of the nucleophile to form a new sigma bond between the nitrogen and the phosphorus, as well as releasing our azide group. So we then react this with our secondary alcohol, which later becomes deprotonated to form the resulting structures here. These steps ultimately make the oxygen in the alcohol a better leaving group for when it undergoes an SN2-like reaction with the azide, producing this final product here. It's important to note that the secondary alcohol undergoes complete inversion of configuration, which explains why the azide group is now on the opposite side of where the original alcohol group was. Thank you for watching.